two talks left, one by Jorge Garza Vargas, who will talk about periodic operators on trees and non-commutative Floquet theory.
Okay, well, thanks a lot to the organizers for the invitation to give this talk, and I'm very happy to be here and see a lot of people that I haven't seen in a while. Okay, so this is joint work with Jess Banks, Jonathan Breuer, Eyal Siegel, and Barry Simon. And so I'm going to tell you about this kind of like line of work, which is basically the study of the spectra of certain operators on certain infinite trees. I'm going to be more precise about this in a bit. But just to give you an idea of what they are, so first of all, they generalize periodic tridiagonal matrices. Those have some very beautiful, well-developed spectral theory. And they're like a significant generalization of it, but they still have a lot of structure, and it's still possible to prove really strong things about the spectral behavior of these operators. And so this line of work has also concrete connections with other areas of mathematics. Maybe most notably for this conference, it's related to pre-probability and sister algebras. Okay, so let me just start by giving you the setting, and please feel free to ask any questions if you have. So in all of this talk, we will work with locally finite undirected graphs. G, so V is the set of vertices, and E is the set of edges. And then we're going to endow the edges with an edge weight. So this is just a function that goes from the set of edges to the set of positive real numbers. And we're going to put vertex potentials. So this means that to every vertex, we're going to associate every number. Okay? So once you have a setting of this sort, you can define an operator, which we will call the Jacobi operator associated to the graph. So this is an operator that acts on little L2 of the set of vertices and goes to little L2 of the set of vertices. And this is the precise way in which it acts. If you think of it as a matrix, then it's much more clear what, or well, it depends where you're coming from, but it's very clear what this is doing. So this is like an adjacency matrix. If U and V are connected, then you put an entry A UV, which is the edge weight of UV in that entry. And for the diagonal, if you put the value of the vertex potential there. Okay? So examples of these operators are adjacency matrices, precisely. So that's when you take these to be 1, the others to be 0. But you can also have discrete Laplacians, or you can have transition matrices for random walks on graphs. Okay. And for this setting, it's particularly important to use this definition, or like this concept appears very importantly. So this is the covering of a graph. Given two graphs G and GC, we will say that GC is a covering of G if there is a surjective map from the set of vertices of GC to the set of vertices of G, such that for every vertex in the big graph, so every vertex in the cover, its neighborhood gets bijected with the neighborhood of F of P. So here's a graph, and here I have a cover. So if you look at any vertex in the cover, this is projecting down to some vertex down here, and you can see that the neighborhood of this vertex is isomorphic to the neighborhood of that vertex, and this is true for all of the vertices. So this is the same notion as topological covering, and also from topology, we will borrow this notion of universal covering tree. So if you have a finite graph, G, there is a unique cover, which is a tree. This is not hard to show. And in fact, you can show that once the base graph G has at least one cycle, then this is an infinite tree. If G is a tree itself, then the universal cover is just G, so that's kind of boring. But once you have a cycle, you start having some more interesting structure on this guy over here. Okay, so combining the two notions I just told you, so if you have edge weights and vertex potentials for your base graph, you can endow now the universal cover with periodic edge weights and vertex potentials in the following way. So if you have a covering map from your universal cover to G, you can pull back each of these vertex potentials, for example, So say I'm looking at this vertex over here. Well, this guy and this guy and this guy and so on are in the fiber of that vertex. I'm just going to put the same vertex potential there, right? So this is somehow repeating what edge labels and vertex labels I have here. You repeat those on the tree, and then you can take the operator of associated to this set of edge weights and vertex potentials, and this is some sort of periodic operator on your tree. So the main question in this line of work is, given a graph G, what can we say about the spectrum of this periodic operator on the universal cover? Okay, I don't know if, depending where you're coming from, this might seem like an unnatural setting and an unnatural question. Hopefully I managed to convince you that there's something here and that there is actually interesting connections to the things that we do. And something that that is useful when trying to answer this question is a set of spectral measures that you can associate to this setting over here. So if you have a vertex V, sorry, a vertex U in V, remember, so V is the set of vertices in the base graph G, you can look at the fiber of that vertex U and choose any element in the fiber. This is going to define some vector in L2 of V of the tree, right? So I'm looking at the fiber of this vertex. I just choose one there. And then there's some canonical vector in this space L2 of VT, which is I put a 1 there and 0 everywhere else. And then once you have a vector, you can define a vector state, right? So this vector state, it's operators and gives you back this number here. This is a positive linear functional. So it's going to induce a spectral measure on the spectrum of your operator JT. So note that even if I fixed U here and U tilde was arbitrary, I'm denoting this measure as mu U, not mu U tilde. And the reason for this is that regardless of what U tilde you choose in the fiber, you'll get always the same measure. And this comes from the fact that if you have two vertices in the same fiber, then there's going to be an automorphism that transports one of them to the other, and then the walks around it are going to be the same, and therefore your moments of your measure are going to be the same. So you'll end up with the same measure. Okay, and once you have these measures, we're going to define the density of states of the tree to be the average of these spectral measures over all vertices in the base graph. Okay, so this is a density of states in the sense of statistical mechanics, where you have some infinite system, in this case being the tree, and then you have bigger and bigger boxes that approximate the system. You see what happens in each box, and then you take the limit. So right now it's not so clear why that's the case, but I'm about to tell you in what sense this is like a density of states. Yes? Yeah, no, we're not taking into account the weight. So the weights basically affect how these mu u's look like, but yeah. Okay, so if you were wondering what this density of states look like, well, and how sensitive they are to changes in the base graph, well, here I put two graphs that have the same set of degrees. So they have 3 vertices of degree 2 and 2 vertices of degree 3. And as you can see, the density of states is quite different for both of them. Now I have here a fixed graph, and I'm going to vary. So in this case, I just took the edge weights to be 1 and the vertex potentials to be 0. I got this density of states. But then if I vary the A's, I get something like this. And once I start varying the B's, the symmetry is broken. I get something like this. Right? And the question is, like, given the graph and given these coefficients, what can we say about these measures over here? Okay, so there's a pre-probability approach to this question. It can take you to a certain point, but then this is really not that this line of work is not a subset of free probability in the sense that at some point free probability becomes more general than what you need, and then it becomes really hard to use free probability to prove certain specific results about this setting. But there's some that you can get kind of for free out of free probability. Okay, so the free probability approach relies on this observation over here, that if you have a graph and you take its cover, then the Jacobi operator here is going to have a structure of this form, where these UIs are permutation matrices. Okay, so basically, if I'm taking a cover of the graph of degree d, so in this case d is equal to 3, the Jacobi operator on this cover is going to be a block matrix of d by d blocks, where each of these blocks, instead of being ones, are going to be permutations. And then if here I don't have ones, but some general edge weights, I'll multiply those permutations by general edge weights. The reason for this is that a block over here, say this one, is going to tell you how a set of vertices. It's going to be scary when I ask a conjecture and series offset. Yeah, if you take a block over here, that's going to correspond to a set of vertices interacting with another, with a fiber interacting with another fiber. And as you can see, there is a matching of this graph between fibers, and those are the permutations that appear over there. Okay, so once you do this, well, then there's a very easy way to construct random covers of the graph, which is like, okay, well, I know that all of the covers are basically taking permutations there. Let's take them independent, and let's take them uniform at random from the permutation group. So a random lift of degree n of the graph G is basically going to be the graph that you get by plugging in here random independent permutations. Okay, so that's a definition. And then we're ready to use free probability, right? So the point here is that if you take the graph G and then you take sequence of random n lifts of G and you let n go to infinity. Okay, so you take this sequence of random graphs. What you can see is that in some geometric sense, these random graphs are going to converge to the infinite tree. Okay, that's called Benjamin-Ishram convergence. And basically what it means is that for most vertices that you look in the cover, if you take for k fixed, if you take a k neighborhood of that vertex, it's going to look like a tree. So this is some type of geometric convergence. But most importantly, it implies that the walks around most of the vertices are going to look like the walks around the vertices in the tree. And therefore, the spectrum of the random matrices associated to these random graphs is going to converge weakly to this density of states. So in that, this is like the analogy with physics that I was telling you about. These random covers are like these bigger and bigger boxes of finite size that are approximating the infinite system. Okay, well then we use this result of Nika, which basically says that these guys converge in distribution to free Haar unitaries. Okay, so this lets us define some infinite dimensional operator, which is going to be the limit of the operators that we get from these random lifts. We know that the spectral distribution of these random lifts converges to the density of states, and therefore the spectral measure of this operator here in this algebra under the canonical trace is going to be precisely the density of states. Okay, so basically I was asking a question about a periodic operator on an infinite tree. It reduced to study the spectrum of this operator, which has free entries, okay, free Haar unitary entries. Okay, so that's basically that's the free probability approach. It turns out that once you view it this way, it's very clear that this is the non-commutative analog of what's going on in Floquet theory. So this is something that started in physics. Here, people study periodic operators, but now on lattices on the Euclidean space. So for example, this is the graphene. There's also some lattices in R3, which are important for crystallography, and very important properties, physical properties, such as superconductivity, can be encoded on the spectrum of these operators, and that's why people care about the spectral theory of this type of operators. So there's two ways to construct universal covers. One is the one I already told you about, so that's like the non-abelian universal cover, but there's also the notion of abelian universal cover. So basically, if you have a base graph, what you can do is you can take a spanning tree of this graph. So for example, here, I took this spanning tree in black, and then you might have some excess of edges. So you're going to call beta that excess of edges. It has this nice formula over here. And now what you're going to do is with scissors, you're going to cut these edges over here. This gives you a tree with dangling edges out of the vertices. And then there's two ways in which you can construct some infinite pattern. So one way is the one that I already told you. So you take the Cayley graph of the free group in this number of generators over here, and then you put a copy of this guy in each of those vertices. And how are you going to glue those copies together? Well, if you take two adjacent vertices in this Cayley graph, they're going to be connected to an edge, and because it's a Cayley graph, it's going to correspond to a generator. But there's a bijection between generators and edges in here. So basically, when you traverse through this edge over here, you're going to look at the corresponding dangling edge, and you're going to connect those. So that constructs, in this case, an infinite tree in the sense I told you before. So this is a universal cover. But if instead of taking the Cayley graph of the free group, you take the Cayley graph of z to the beta, then you get a lattice over here. And then when you do this kind of construction, then you'll get pictures like the ones I showed. So you'll get something like the graphene, or you'll get something like crystals and so on. Now, here, a consequence of Floquet theory tells you that for the corresponding operator on the abelian universal cover, there's a very nice description of the spectrum. Namely, what you're going to do is you take the Jacobi matrix of the graph, and you're going to throw in faces for each of the edges. And then those faces, you allow them to vary in the torus, and the spectrum is going to be the union of the, this is a bad typo. Here it should say spectrum. Yes. Okay, very bad typo. So the spectrum is the union of the spectra of all of these operators. And what this is doing is parametrizing points in your spectrum by points in the torus in this like nice way related to the graph. Now, spectral theories don't say it this way, but basically what the density of states is in this case is you take the Jacobi operator on the graph, and then you throw in random Haar unitaries, but now they commute with each other and they're classically independent. Okay? So if you take them to be classically, then you get Floquet theory and these periodic operators on lattices. If you take them to be free, then you get periodic operators on trees. And we're interested in studying the periodic operators on trees, where such a description as this one is not available. Okay? And the thing is that not only the points in the spectrum, but also the eigenvectors can be nicely parameterized by points in the torus. So this is like a very explicit description. Okay, so just to give you an example of this like non-commutative Floquet theory, this is a result that was implicit in the work of Tsunada from '92. So if you have G, a base graph, with P vertices, then turns out that the spectrum of the periodic operator on the universal covering tree has at most P connected components, and if you measure each of these connected components under the density of states, that's going to be an integer multiple of 1 over p. Now, before, well, until recently, the only known proof of this used K-theory. I'm sure that some of you will already find this trivial, because I told you that this the spectrum of this operator you can view as the spectrum of some operator where you're basically plugging in free hard unitaries. You can take those free hard unitaries to be the generators of the reduced C-star algebra of the free group, and then use this result of Pimsner and Voiculescu, which says that K0 of that C-star algebra is Z, and then there's some very standard mechanism on how to show that the mass of these connected components is an integer multiple of 1 over p. However, then if you want to go and prove things, for example, about the point spectrum, or prove other things about the absolutely continuous part, then you have to go to kind of like even sometimes like a different field, or like exit C-star algebras and try some different technique and prove that. So I guess the point I'm trying to make is that this is something that's true in the abelian case, but in the abelian case, there's a unified theory to explain all of these things. And here, almost everything you take from the abelian case turns out to be true in some form in the non-abelian case, but you have to invent some new way of proving it. And what we're trying to do is to find a unified approach to this. So recently, we found a self-contained elementary proof of this fact that circumvents K-theory, and which also allows for the analysis of other characteristics of the spectrum, such as the point spectrum of the periodic operator. We still can't get everything that's known from this formula. Actually, we can just get a modest amount of things, but this gives us hope that maybe there's a way to That's a good question. I don't think so, because you're only so you're dealing with a matrix that has basically the generators in the entries, whereas this is a statement about, say, like arbitrary polynomials in those generators. So you're proving it for a subclass, I guess. Yeah. Yeah. And so we did this through a formula that we obtained for the integral of log z minus t. So we related this to Cauchy transforms of certain subtrees of t. So this is something that's available in the case where the base graph is a p-cycle, in which case the universal cover is an infinite line. And in that case, your operator jt is just a periodic tridiagonal operator. And there's a lot of techniques there. Among them, there's the Stylus formula, which expresses this in terms of some Cauchy transforms. But we found a generalization of that for subtrees. And okay, maybe I have 2 more minutes, so I can tell you maybe a bit of what those Cauchy transforms are. So if you write the operator in this way, you can decompose this as a sum of matrices that are free with amalgamation. So one term is going to correspond to just taking these 2 and 0 everywhere else, the other term taking these 2, 0 everywhere else, and so on. They're obviously free with amalgamation over the full matrix algebra, but you can in fact prove that they're free with amalgamation over the diagonal. And then if you leave one out, that one is going to be, if you leave one of these terms out, that's going to be free with amalgamation with respect to the sum of the others. And then you can define some subordination functions, and those subordination functions are precisely which gives you the Cauchy transforms of the formula that we have for this guy. We don't need free probability for this construction. But since this is a free probability conference, I can tell you what these functions are in free probability language. Okay, so currently the most, basically the main problem is to give an effective characterization of the spectrum of this guy. So for the case of abelian covers, I already told you a very effective characterization of it. And a way to test if your characterization is effective is to answer if this conjecture is true, and even if it's not true, how true it is. So the conjecture says that for any graph G, the set of edge weights and vertex potentials for which this guy has exactly the maximum number of connected components, so basically all gaps in this set of bands are open, has full measure. I actually think I'm dubious about this conjecture, but I do think it's true to some generality. Okay, so that's all.